This video focuses on a tutorial of the JASCO V630 ultraviolet visible spectrophotometer. In the context of the analytical experiment that you folks will be doing, the instrument will be used to do a quantitative analysis of phosphorus in the form of phosphate by forming a colored compound in the presence of molybdate ion in acid called 12-MPa. 12-MPa itself is not brightly colored in the visible part of the spectrum, but we can make it colored by placing it into its reduced form. So we do that by adding a reducing agent to the reaction mixture, which will be ascorbic acid. So first, just a quick review of the instrument here. As I mentioned, it's an ultraviolet visible spectrophotometer, which means that it has to include a visible and also an ultraviolet source. The source would be housed in the rear of the instrument here. And technically we would have a visible source, which would be something like a tungsten halogen lamp, and also an ultraviolet source. And that ultraviolet source most likely would be a deuterium lamp. From there, we have a sample compartment and a monochromator. The sample compartment looks like this. We actually end up having two cuvette holders in the sample compartment. The rear cuvette holder is for the reference, and the forward one here is for the sample. Now the reason for this is because this instrument is a double beam in space instrument, which means that what we're going to be doing is separating in space the light passing through the reference side and the sample side. Now, to be able to do this, we have to have two detectors. So we will have two optical detectors here, and those detectors have to be balanced to work well. And a diagram of an instrument like this will be found in your experimental handout, so that's very well worth reviewing. Alright, so coming up to the instrument, I have it on right now, but if it needed to be turned on, that can be done by flipping the rocker switch, which we find down at the bottom right panel of the instrument. And provided we are into the software here, we'll come to the desktop. Now to log into the computer to get full access to the software that you'll need, you'll probably have to come in as me. So if we're not previously signed in, come find me so that we can sign you in to have complete access to the software. So we're going to want to look here for the Spectrum Manager 2 icon, which we'll double click on, and that will bring us into the instrument software here. So this is going to be the top level of the software, where you can see that we have a menu here for the type of experiment that we want to do. Alright, so at this point, the first thing that we want to do is to actually balance the two detectors. Now this isn't mentioned in the procedure, but it's a good idea to do that. So what we're going to do is we're going to move into the spectra measurement mode here, which means we're going to be acquiring a spectrum. Okay, so we're initializing the application here, transferring the parameters and setting everything up. And here we are. So the next thing we do is we go into the measurement option here. And what we want to do is to make a measurement of the baseline. Now again, what this is going to do for us is to allow us to balance the two detectors so that there won't be an offset between the reference side and the sample side that will be carried over into our absorbance measurement. Now the thing to remember before we do this is to open the door here and make sure that there is nothing in the cuvette holder. Neither cuvette holder should have a cuvette in it. Alright, so once we've ensured that, we're going to go ahead and click on the measure button here. And now we're going to run a scan here. Now notice that the scan is being run between 400 and 800 nanometers. Now that's worth actually checking before we run the scan, but those should be the default parameters. If not, we would go back into the measure and parameters option and we would change that if need be. So what we're doing is we're scanning across the entire visible part of the wavelength range. What you'll notice here is that you have a peak here that corresponds to an internal filter change. And again, that peak would show up as a deviation in our absorbance spectrum if we don't correct for it. So doing a point-by-point, wavelength-by-wavelength balancing of the two detectors should null that effect out. Alright, so we will actually let the scan continue and allow it to finish here. Again, we're scanning between 800 nanometers and 400 nanometers, which is the wavelength range of the visible part of the spectrum. Again, if that wavelength range is not previously set, we need to go back into measure and parameter and set it accordingly. Alright, so we're almost done here. So essentially what we're measuring here is percent transmittance as a function of wavelength. So what we're really looking at is the output of the source across that wavelength range balanced across the two detectors. Now the next thing that we want to do is we want to actually measure the spectrum of the reduced 12 MPa. So at this point you will have taken your most concentrated sample. You will have prepared that by adding the ascorbic acid to it, and you will have allowed the blue color of the reduced 12 MPa to develop. So I've already done that, and that's ready to work with. So let's go ahead and load the sample at this point. So we'll come back around here to the sample compartment, and you'll notice here that I have a couple cuvettes. The cuvette in the back will contain the reference, which is everything except the analyte. Notice that it's clear and colorless. We're going to place it into the rear cuvette holder here, and notice that I place the transparent side in the path of the beam, and notice that the path of the beam moves across the instrument like this. The opaque side of the cuvette should be facing me as I stand in front of the instrument. Likewise, I'm going to come back and load the sample cuvette, which has the 12 MPa reduced already in it. You can see the nice blue color of the reduced 12 MPa product. So I'll place that into the sample holder of the cuvette, or rather the sample holder for the instrument. Alright, so reference in the rear, sample in the front. We'll close the door, and we'll come back to the measure option. Now again, I just want to double check the parameters. We could have again done this before we did the balancing of the detectors. But let's just check and see what we have here. We're going to be working in the absorbance mode, which is what we want. Our response will be fast. We're scanning at 400 nanometers per minute. That's fine, we'll work with that. And most importantly, we're scanning across the visible part of the wavelength region, 800 on the red side down to 400 on the violet side. And we're going to be looking at a data interval of 1 nanometer, which is the resolution of our spectrum. We'll also be in the continuous scan mode. Alright, so we can go ahead and save that. Alright, so that's been saved, and we can say OK. Now at this point, to actually start the scan, we can either do it through the software, or we can come back around to the instrument and we can press the start button. If we press the start button, now we can come back to the screen here and we can see the absorbance spectrum start to develop. Now in this case, my 12 MPa has been sitting around a little bit, so my absorbance spectrum is going to be maybe a little bit different than the absorbance spectrum that you are going to see. Normally the peak that we would see for a fresh 12 MPa sample will be shifted with the peak a little bit further into the visible part of the spectrum, but this will be fine for what we wish to do. Alright, notice again that what we're measuring is absorbance, in this case, as a function of wavelength. So when the spectrum finishes acquiring, what we're going to see here is that we're going to automatically move into a spectral analysis mode. So we can leave the spectral measurement mode here, so I'm just going to X out of it. I don't necessarily want to save it, you may. And now we're into the spectral analysis window. and that's left behind. So what I can do is I can do a left mouse click here, and that puts a cursor down there, and I can move that cursor back and forth. So what I'm going to do is just pick a wavelength around here where I know that I'm getting good absorbance of the 12 MPa reduced. Now again, your peak will probably be shifted a little further to the left here, so it will be easier for you to identify a lambda max. So I'm just going to pick a region here where I know that the compound absorbs. And notice that the wavelength is given to me as I move the cursor back and forth. So I'd say I'm going to work right around 715 nanometers. That looks like a reasonable place to be because we have a high absorbance there. Okay, so I'm going to remember 715 nanometers, or write that down as my maximum wavelength of absorption because I'm going to need it a little bit later. All right, so we can move back out of here. We don't need to save this unless you wish to. And now I can click back into the main menu here. Now, before we actually start the analytical part of this experiment, the quantitative part, which is where we're going to be developing a standard curve, what we're going to be doing is we're going to be determining the slope at a given wavelength of absorption as the blue 12 MPa reduced form is generated as a function of time. So this is a kinetics experiment, okay? So as a result, what we're going to find is that the rate of the reaction, or the slope of the absorbance versus time curve, is going to increase as the concentration of the phosphorus in the form of phosphate also increases. So based upon that slope, we can generate a standard curve that we can use to then determine the concentration of an unknown phosphorus sample. All right, so we want to work with a time course measurement. So let's go ahead and set that up. I'll double click on the time course measurement here. We'll let the application initialize. And note here that the wavelength is set at 720 nanometers. We can go in and change that. I think I chose 715, so if I want to change that, I can do that. And I also want to just check my parameters anyhow. So I go to my parameters option under measure. And notice that I'm going to be working in absorbance. I want my wavelength now to be 715 just because that's the wavelength I chose. Yours, of course, is going to be different based upon the lambda max that you measure. I'm going to start at 0 seconds, and I'm going to let the blue compound develop across 2 minutes or 120 seconds, and I'm going to plot the absorbance as a function of time at a wavelength of 715 seconds, or rather 715 nanometers. The data interval, or the time between data points, will be 1 second, and that default value is fine, so we'll say OK here. Okay, so all the parameters have been transferred, and now we're ready to go. So the next thing that we need to do is we need to come back and prepare our sample. So I'm going to bring the cuvettes back out. I'm going to leave the reference cuvette in because that won't change, but the sample cuvette can come out. And what I'm going to do is I'm going to dump that into a waste beaker. The next thing I'm going to do is grab a little bit of distilled water. And I'm going to rinse the cuvette a few times just to take the old sample out. Rinse and into waste. I'll do that 2 or 3 times. Okay, just to ensure that we have a clean cuvette here. Okay, shake the cuvette out a few times just to make sure that we can get as much of the liquid out of it as we can. And now, I am going to prepare to set up the sample. So the first thing I need to do is run down the hall real quick. And I need to obtain, I'm going to go this way so I don't have to wear a mask, the ascorbic acid. I forgot the ascorbic acid. So we'll get the ascorbic acid. Pardon me for this, I don't want to splice the video. And by the way, if you need to obtain the ascorbic acid, it's going to be in the refrigerator back here in FSC 302. However, I should have it out for you if you need it. There it is. And we keep the ascorbic acid refrigerated over time because it has a tendency to decompose if we don't. And this way we can keep it fairly fresh throughout the remainder of the semester. All right, so we have our ascorbic acid here, so we're ready to go. So what I'm going to do is look at one of the standards here. So I'm going to look at a standard you will have made up. Now, the standard would have been made up in a 10 milliliter volumetric flask. Now, what I've done is I've transferred the standard actually to a small beaker here. And the reason for that is because I need to pipette exactly 2 milliliters out. I'll be using a standard 1 milliliter auto pipette to do that. Set it at 1,000 microliters, so I'll need 2 dollops of that. Now, the problem, of course, is that I can't actually insert the tip of the pipette into the little volumetric flask here. So what I'm going to do is I'm going to transfer to a beaker here so I can get the tip in. All right, so I'm going to pull out down to the first stop, 1 milliliter, and that's going to be transferred into the cuvette all the way down to the second stop. Okay, we'll come back for our 2nd milliliter here. And again, we're going to transfer that to the cuvette down to the 2nd stop. So now I have exactly 2 milliliters of my standard in there. Now I'm going to need a couple of hands free to do this, so I'm going to set the camera down for a moment. All right. And I'm going to go ahead and focus it down here so you guys can see what I'm doing. So I have my ascorbic acid here. To initiate the reaction, what I'm going to do is I'm going to place exactly 100 microliters or 1/10 of a milliliter of ascorbic acid into the sample I just prepared. And I'm going to do that using this auto pipette. So down into the ascorbic acid, pull up 100 microliters. There we go. I'm going to place it directly in here. I'm going to plunge it down a few times to mix. Then if you want, I can take a little bit of parafilm, invert that, and now we're going to place this quickly back into the sample container, or rather the sample side. All right, close the door, and now we're going to start the experiment. Here it goes. It's asking me if I want the blank to be measured. Nope, I don't. And now the experiment is running. Okay, so we can actually see the absorbance changing rapidly as a function of time here. So the absorbance is increasing in a more or less linear fashion as a function of time. And that's how we're going to generate our standard curve. So we're going to allow this to go out for a full 2 minutes, although we probably won't be able to utilize the data across the full 2 minutes because we will start to see a deviation from linearity at long times. The reason for that, of course, is the fact that we're starting to run out of our limiting reactant, which causes the reaction then to slow down. So we'll let this go ahead and run out. All right, and you can start to see that little bit of deviation from linearity here. So what that means is that when we choose the linear region for initial rates, we're going to be working at shorter times here. And we're close to being done. A few more seconds. So again, this is going to represent a data point on our standard curve. So you'll be generating curves like this for all of your standards, and you'll also obtain a curve like this at the same wavelength for your unknown prepared the same way. Almost finished. Okay, so now what we can do is we can leave this mode here. I'm looking to see whether it gave us a, maybe it's down here. Here we go. It looks like it dumped the spectrum down to the toolbar down here, so I had to pull it back up. But we're back now into the correct mode for data analysis here. So now we see some options up here. So we want a processing option here. So I'm going to choose processing, and I'm going to look at common options. And under common options, I want kinetics. Now when I do that, you're going to notice that there are now two vertical lines. So what I can use is I can use those vertical lines to define a linear region. So I'm going to take my cursor here and I'm going to grab the box, and notice that it turns into like a paper clip, and I'm going to move it to a time very close to the origin here. Now I'm going to take the second one and I'm going to move it also to the left until I get something that looks like a linear fit, or something close to a linear fit. So you can see now that we have something that's almost linear across that range. Now once I've defined that linear region at short times, I can now move across the screen here and notice that I can pick off a slope, which is the top line here. So it's change in absorbance per minute. So in this case, our slope will be 0.2216, which will be the y value on your standard curve. So that is the slope expressed in change in absorbance per minute. So I can use that again to generate my standard curve for that specific concentration. So again, you're going to do this for each one of your standards, and then you're going to come back and do this for your unknown so that you can generate a standard curve. Now, to shut things down, very simple. All we're going to do is X out of everything that we see here. It will ask you if we want to save things. No, we don't need to save anything. Again, if there's anything open at the toolbar at the bottom, generally I like to back out until I know that I'm all the way back into the main menu. So anything else I see open down there, I'm going to get rid of. Now, once I'm here back in the main menu, I can X out of that. And if it asks me if anything else is running, we'll come down again and we're going to find anything else that we can back out of. We're going to get out of it, and from there we should be able to exit, and again we're terminating the drivers and heading out. So once we're out of the software, the last thing to remember is to turn the instrument off and make sure that you have removed the cuvettes from the compartments in the instrument. And beyond that, this should conclude the demonstration of the JASCO V630 ultraviolet visible spectrophotometer. Close the sample door and we are finished.